Okay, so today we're going to start looking at solving linear quadratic systems. And this is very related to a unit from grade 10 math called linear systems. And in linear systems, we would have two equations of lines. So that's what we're going to start with. We're going to review that. So here we have an equation of a line, hence linear system, 3x plus 1. And we have another equation for a line, y equals 2x minus 3. And ultimately what we're trying to do is we're kind of trying to find the intersection of these two lines. And you probably did that in grade 10. You probably did that graphically sometimes. But what we're going to focus on today is algebraically. So how we algebraically solve for the intersection. And intersections of things in general that we're writing equations or functions for is that at the point of intersection, the x value is common to both the equations and the y value is common to both the equations. So they have the same values at their point of intersection. And it's usually, with lines, there's usually one point of intersection or 0 points of intersection, or they are the same line, can sometimes happen. In this case, we can tell they aren't parallel because they have different slopes, but that's not going to be important to recall too much. So the process is we rearrange them both to equal y, which is done for us here. And then we set the equations equal to each other. So we're going to set 3x plus 1 equal to 2x minus 3. Okay, and now our goal is going to be to solve for x. So a good strategy for that for linears is to bring everything with an x to one side and everything without an x to the other side. So what we might do here is we might bring this 2x to the other side. So we're going to have to subtract it. So we'd get 3x minus 2x because it's adding over here. It's plus 2x here. So we've got to bring it over minus 2x. And we want to bring the 1 to the other side. So we'll have to subtract it to the other side. So minus 3 minus 1. Okay, and now we'll collect like terms here. Oh, and we just get x equals -4. Okay. So we've got x as a number. Okay, sweet. So that means that this is the x value of our intersection point. And the next thing we need to do is an intersection is a whole point, not just an x value. So we need to know what the y value is. And we can plug that in, this x value, into either of our starting equations. It doesn't matter which one. In fact, you can try them both on your own and see that you get the same answer. I'm going to choose the first one here. So the y value is going to be 3 times our x value of -4 plus 1. So that's going to be -12 plus 1 equals -11. And that's our y value. Okay, so we found the intersection. So we'll say, therefore, intersection at -4, -11. All right. So hopefully that process seems a little familiar to you. You probably did some other things. Sometimes with linear systems, you learn some other strategies like elimination. So maybe you add or subtract the equations and stuff like that. That's another strategy that works perfectly fine. This version would be known as substitution. Right? You may remember those two things. Both would work for this, and both would actually work for the thing we're going to learn when we do linear quadratic systems. You can actually do elimination. It's not as pretty and not as nice, so we're not going to do that. We're going to do substitution. Okay, so the process is the same for a linear quadratic system. So we know how to solve linear systems. We set the equations equal to each other, the y's equal to each other, right? So 3x plus 1 equals 2x minus 3. And then we solve for x. And then we take our x value, we plug it in to find the y value. And that's our point of intersection. The process is exactly the same in general. The specifics are slightly different. So let's see how that works. We're going to start by setting our two equations equal to each other. They're already y equals. So we'll go 3x plus 5 equals x squared plus 7x minus 7. And now we want to solve this for x, but it's a quadratic. We have an x squared somewhere. So just bringing all the x's to one side and all the non-x's to the other, that's not going to work so well. We're going to have to use some of those strategies we've learned for solving quadratics. And the primary strategy for solving quadratics is that we want to rearrange this so that it equals 0, and then we can do things like factoring or the quadratic formula to solve it. Okay, so I'm going to write that in red as a little note. So rearrange to equal 0. So in order to do that, we're going to have to bring the 3x over and the 5 over. Okay, so we'll get 0 equals x squared plus 7x. Bring the 3x over, subtract it over, minus 3x. Minus our 7, and then we have to bring the 5 over, and we're going to have to subtract that on the other side, so minus 5. Okay. So now we want to simplify this a little bit. This looks a little too bloated. Let's collect some like terms. So we've got x squared, 7x minus 3x. Collect like terms, that's 4x. And negative 7 minus 5, well, that's negative 12. Okay, and now all we need to do is we need to solve this quadratic for x. And we know how to do that. We could use the quadratic formula, of course. And if you use the quadratic formula for this question, that would be a-okay. But I'm going to solve this by factoring because I think I can factor this one. Okay, and because we haven't really talked too much about solving by factoring. But let's factor this. So I need two numbers that add to 4 multiplied to negative 12. I think positive 6 and negative 2 would work. Okay. Now, to solve this from this step, what we do is we split this into two terms. And we say, well, one of them would be x plus 6 is 0, equals 0, and the other one is x minus 2 equals 0. And we want to solve each of these independently, so we just bring the number over. So here we get x is negative 6. That's one of our x values. And here we get x is positive 2, which is our other x value. Of course, if we did the quadratic formula from this step here, we would have gotten two answers as well, and you'd get the same two answers. Okay, so, let's think. We got two x values. That means that this line in this parabola, or this quadratic, they intersect twice. Does that make sense? Well, let's think about this for a second. I'm going to draw a little sketch. So we got a positive parabola, so it opens up something like that. And we got some positive slope line. So if I draw a positive slope line, well, look at that. Yeah, they would intersect twice, right? So we have an intersection here and an intersection here. So that's why when we're solving this, we're getting two answers, because a line and a quadratic intersect twice. So we still have to find the y values. So let's do that. So when we plug in, once again, you can plug into either equation to find the y values. You'll get the same answer because these are the x values of the intersection. I'm going to color code this to keep them separate, but later on we'll use function notation, which will actually help us stay a little more organized, which will be nice. You can plug into either. The line's a lot easier. So we're going to do the line, or I'm going to do the line. You can do whatever you want. Y equals 3 times negative 6 plus 5. So that's negative 18 plus 5. Y equals negative 13. So that's one of our intersection points, negative 6, negative 13. And let's go with green here. For our other one, y equals 3 times 2 plus 5. 6 plus 5 is 11. Okay, so we should write a little conclusion here to show our 2 points. So therefore, two intersections at our first point we found was -6, -13, and 211. Now, it doesn't matter what order you write these in, but it is very important that we match the x with the corresponding y value, right? It would be wrong to say -6, +11, and 2, -13, because those aren't the correct corresponding xy pairs of 4 points. Okay, so that's the general process. But now I'm thinking about it. We had 2 intersections here, which made sense, but are we always going to get 2? And let's think about that for a second. So how many intersections can we get in a linear quadratic system? So the first one we've already seen is 2 intersections. Okay, so what would that look like? Well, that would look like a parabola. We're just going to draw a really generic parabola and a line crossing through it. Okay. Of course, the parabola could be inverted upside down, or the line could be sloped differently. It could be a horizontal line. It could be a vertical line. Maybe it couldn't be a vertical line. Let's talk about that. If it was a vertical line, would it intersect twice? No, I think it would only hit it once, right? And that actually is a little bit tied to our vertical line test for testing for functions. Quadratics are functions, so vertical lines only touch them once. One intersection. So we could have a vertical line. And there's actually another way we can only have one intersection. Okay. So if we have a parabola, we could have a line, and this is going to be very hard for me to draw on this pad very well. But it goes like this, and it touches one time. Okay. This is called a tangent line. Okay. Tangent. Okay. So a tangent line kind of like goes and just like kisses and touches the line. And we've actually seen this in the past when we've done, for say the equation y = x squared, it comes down, it hits the origin and bounces off. It hits the x-axis and kind of like skips off in a way. So we have horizontal tangent lines, but you can actually have slope tangent lines as well. Okay. Let's try, what about 0 intersections? Could we have 0? Yeah, we could. So we could have a parabola, and the line could literally just miss it. Of course, these lines, all these lines and parabolas go forever. I'm not drawing all the arrows, but okay. So we could just have 0 intersections. Okay. So how on earth would we know this, though? If we're going through this process of solving our linear quadratic system, how would we know if we're going to get 2 answers, 1 answer, or 0 answers? Well, you may be able to guess, but we actually have something about quadratics that tells us how many solutions we get. And if you look at this step right here, well, this is just a quadratic where we're trying to solve it. So the discriminant is tied to this. Okay, so the discriminant. So if we look at the discriminant and we're going to get 2 answers, it's going to be positive. If we have 1 intersection, well, that's the same as 1 solution. So that would mean that the discriminant is 0. And if we have no intersections, that would be because we have a negative discriminant. Okay, so the discriminant can tell us how many intersections a linear quadratic system is. Now, it's important, we wouldn't be doing the discriminant of the quadratic. We would be doing the discriminant of the quadratic once we've combined our equations. So we'll do an example of that in a little bit. Okay, I'll leave this up because I feel like I've been scrolling off it a bunch. Or you can pause the video, I guess. I'm going to go to the next page. All right. So we want to find the intersections of these 2 functions. So this time we're using function notation. It doesn't really change anything. So f of x is equal to 2x minus 3, and g of x equals -2x squared plus 5x minus 8. So notice that it's quadratic. It's got an x squared in it. This is a line. Okay, so the process is the same. We're just going to set them equal to each other, and then rearrange, and then solve for x. So let's do that. Switch to a different color here. So 2x minus 3 equals negative 2x squared plus 5x minus 8. Okay, so we're going to want to rearrange this. So we'll get 0, negative 2x squared. So we're going to have to subtract the 2x over. Minus 2x. And then we have our negative 8. And then we have to add the 3 over. So plus 3. Okay, let's simplify. Negative 2x squared plus 3x plus, nope, not plus, that's a minus, I think. Minus 5. Minus 5. Okay, so we want to solve this. Maybe we could factor that. That looks harder, though. I think we're going to want to try to do the quadratic formula. But before we do the quadratic formula, let's check the discriminant. Okay, so let's write down discriminant. You could abbreviate that if you would like to, just like disc or something like that. So discriminant, so that's b squared minus 4ac, right? Quadratic formula is, just to refresh everyone's memory, x is negative b plus or minus the square root b squared minus 4ac, all divided by 2a. And the discriminant is the piece under the square root. So in this case, it's b squared, which is 3 squared minus 4 a c. Okay, so we're going to get 9. This we might need a calculator here. That's a positive 10 there, minus 40. I think we're going to get a negative here. Look at that. So we got a discriminant of negative 31. So what does that mean? Well, that means that there's no solution to this quadratic, which means that there's 0 intersections of this line in this quadratic. So we don't even need to do the rest of the quadratic formula. I'm going to say, therefore, there are no intersections. Okay. Now, if you had just plugged straight into the quadratic formula instead of doing the discriminant, that would have been fine. And you would have just gotten a negative 31 under the square root. And you would have just come to the same conclusion, that there are no intersections for this linear quadratic system. Okay, so let's do this last one here. So for these two functions, we got a line again and a quadratic again. Okay, predict the number of intersections using the discriminant. Okay, we know how to do that. And then find all intersections that exist. So if none exist, we'd say for part B, we'd just say like there are none. Okay. If there's 1, we'll find that 1. If there's 2, we'll find both. Okay, so let's go through the process. So negative x plus 9 equals x squared plus 3x plus 13. So we want to rearrange it to equal 0. So we're going to want to add that x to the other side. So we get x squared plus 3x plus x, and we want to subtract that 9 over from the left side to the right side, so minus 9. Collect like terms, x squared plus 4x plus 4. Okay, so we want to predict, so you could factor this, or you could use a quadratic formula right away, but it wants us to predict, so let's predict. So to predict, we don't just like use our psychic mind, we do some math. So we're going to do the discriminant. So the discriminant is 4 squared minus 4 times 1 times 4. And, well, that's going to be 16 minus 16, which is 0. So what does that mean? Well, it doesn't mean that there's no answers. It means that there's exactly one answer. So our prediction, therefore, is 1 intersection. So now we need to find the intersection. That's part B. So let's find the intersection. So we could use a quadratic formula. We already solved a big part of it, right? So, not that. So x equals negative b. So remember, we aren't using this quadratic. We're using this quadratic. Okay, so negative 4. We always want to be using quadratic formula with an equation that equals 0. Plus minus the square root of 0. I already know what the discriminant is, so I don't need to rewrite that all in. Over 2 times a. And a value is 1 because there's an invisible 1 in front of the x squared. Okay. So here we're going to get negative 4 plus minus 0. Well, that's all the same. Over 2, which is negative 2. So that's our x value. And now I want to plug it in. We have our two equations up here. It doesn't matter which one we use. I'm going to use the line f at negative 2. So one of the nice things about using our function notation here is we're going to keep the x value along with our solving. So if we had what we were solving for 2 y values with 2 different x values, it'd be a little easier to keep track. Also, it's easier to know, I can tell which of the 2 functions I plugged into, because we have f of x and we have g of x. Now note, we've mostly been using f of x. The g doesn't make a difference. It's just a label. We could put any letter in front of here we wanted. Okay, so we're plugging in here. So negative of negative 2 plus 9 is equal to 2 plus 9 is 11. Okay, so that's our point there. So therefore, 1 intersection at negative 2, 11. All right, that's it for today, guys.